Okay, guys, so we're going to start by looking at the reaction of halogenoalkane today, and we're going to begin by looking at the reaction of these with sodium hydroxide. So this involves what we call a nucleophilic substitution reaction, and what we're going to have here is the sodium hydroxide, which is dissolved in an aqueous solution. It's going to react with this halogenoalkane, in this case iodomethane. So what you'll produce here is an alcohol. And so here we're going to end up making methanol, H3OH, and we'll also make a sodium halide, NaI. And we do this under reflux conditions. We'll talk exactly what that means in a minute when we come down here. So you'll need to know the mechanism for this process and exactly what goes on here in terms of the movement of the electrons. That's a two-stage process. So to begin with, we're going to have the sodium hydroxide reacting with the halogenoalkane. Now, I'm going to mark the dipoles on this halogenoalkane to start with. So the halogen is obviously more electronegative than the carbon, and so electrons are moving in this direction in this covalent bond, making this partially negative and this partially positive. And this permanent dipole rather is not a massive dipole. Iodine is not the most electronegative of elements, but it's enough for that carbon to become quite attractive for that sodium hydroxide. So we can show, therefore, an attack of this sodium hydroxide on this carbon. So we're going to show our curly arrow starting from the negative charge on the hydroxide ion, and the two electrons, double-headed arrow, remember, indicating two electrons on the move, and they will end up in that space between the oxygen and the carbon there, where a covalent bond is about to form. This carbon, however, can only form 4 bonds, and it's about to form a 5th bond with that oxygen. And so the electrons that it has in this covalent bond both move on to the iodine over there. And so the result of that will be this slightly odd situation where the oxygen is in the process of bonding to the carbon, and the carbon is still partially bonded to the iodine. Now this is a transition state, and it's going to be very short-lived, and in fact in many textbooks you maybe wouldn't see this at all. I'll show you in a minute what you might see. And so the results then, what will hopefully would happen would that this bond will form completely to give us our alcohol, whereas this carbon-iodine bond will break completely to give us our I-. And as you can see, the Na plus from there is a spectator ion. Draw that here, still joined together with the I-, and the Na plus here again, spectator ion, is going to join up with this intermediate here. And so, as I said, this is a nucleophilic substitution, the OH minus being our nucleophile here, and it's substituting itself for that iodine. We end up with the OH where the iodine was in place. So if we look through this then, so due to the highly electronegative nature of group 7 elements, iodine being more electronegative than carbon, the carbon-halogen bond has a permanent dipole. The carbon atom in this bond is partially positive and is open to attack by nucleophiles. And here's our sodium hydroxide as a nucleophile, such as the hydroxide ion. This generates an unstable and short-lived intermediate. This is our intermediate. We can label that if we like. Intermediate. As I said, in some textbooks, you wouldn't see that being drawn at all. Quite often, how you might see this reaction might be a bit like this. It might be shown as OH minus with, say, halogenoalkane here, lone pair electrons coming in, forming a bond between the carbon and the iodine. You might want to show your dipole moments on there, that iodine carbon bond breaking, and the result of that being the alcohol and the I minus, with the intermediates that we showed here being absent altogether. Okay. Right then, step 2 then, as the carbon-oxygen bond continues to form and the carbon-halogen bond continues to weaken, the intermediates from stage 1 will eventually form the product. In this case, namely methanol and sodium iodide. If you were to choose halogen here, we obviously could have fluorine or chlorine or bromine or iodine. Iodine is always preferred, and we'll talk about why down here in a second. Okay, so we talked about this being a reflux process. Now, all that means is that we need to heat this mixture up. But the problem with organic compounds is if you heat them up, they're quite volatile. And if it's just allowed to be heated up in an open flask, you turn it back and come back 10 minutes later, it's not there anymore because it's evaporated into the air. And so to stop that from happening, we use a reflux situation where this is our reaction mixture bubbling away here. Reaction mixture, so that in this case that will be our iodomethane and sodium hydroxide, aqueous sodium hydroxide solution. Now this is our heat source. Now we very rarely use Bunsen's because organic compounds are very flammable. And so we try to avoid the naked flame. So a hot plate or an oil bath or a water bath, depending on how hot you want it to get. Obviously with a water bath, 100 degrees Celsius is the hottest you're going to get. With an oil bath or a hot plate, obviously you can get so much hotter temperatures. Your mixture is bubbling away down here, boiling away, and the vapors are moving up. Now what we want is to catch those vapors and stop them escaping. So we put cold water running into here. And that cold water will circulate around this like a jacket and leave out here. So water's leaving there. It'll be a little bit warmer than it was when it went in, but not too warm. And then what we're going to have here is condensing vapors. And so what that means is that because they've condensed, they've turned back into a liquid and they're going to fall back into here. So often you'll see drips falling back down. So it's a constant evaporating and condensing situation. So you can be heating that up as long as you like, and you're not going to lose any of your organic compounds. Whereas if you didn't have the condenser there, the organic compounds would just go up into the air and leave your flask. So that's refluxing. So a nucleophilic substitution reaction like this one is normally carried out using a reflux apparatus, allowing boiling of the mixture without loss of the solvent. Okay, so the next part here is down to reaction speeds. Now, we want our reactions to be nice and quick, obviously. We don't want to be waiting around for them. And to do that, what you would need here is to have an iodine atom linked to your halogenoalkane. Now, there are two sort of arguments that you could think of this here. Now, if you had a fluorine there, that's very electronegative. And so I've tried to show a big delta minus here and a big delta plus. There's a big dipole moment in this bond. And as you go down group 7, your dipole moment's going to get less and less. Now, some people might argue, well, a big dipole moment means the carbon's really positive, and so the hydroxide ion is going to really be attracted to it. Well, that's one way of thinking about it. And you might think in that case that the CF bond was your preferred bond here in order to get this reaction to go, that being a big dipole moment. However, what we actually find is that the CI bond is the best bond for it to go, even though this is a tiny little dipole moment we've got here. The key thing about this reaction is the strength of the carbon-iodine bond. And as we move down this list, these bonds get weaker. Short bond, strong. Longer bond, slightly weaker. Longer bond again, slightly weaker again. Iodine's a big old atom, and it's a long way from the carbon here, and that makes for a weak bond, and that is the deciding factor here. not so much the bond dipole. So what we need to make a note of here is that even though the dipole moment in CI is small, the bond is weak. And breaks easily. So that is what you want if you want this reaction to be fast, not that. Okay. Right then, guys. So 3 more bits we need to know about here. So an elimination reaction. Now, this is another reaction between a halogenoalkane and a sodium hydroxide. Now, you might think, oh, well, we've already done this here, halogenoalkane and sodium hydroxide. But there's a subtle but important difference in this reaction. Here, the sodium hydroxide is dissolved in ethanol, whereas here, it's dissolved in water. Now, you might think, oh, what difference does that make? It makes a big difference because you get a completely different reaction. Because what happens here is that hydrogen and bromine get eliminated. They get knocked out of this halogenoalkane. And so what you'll end up with is an alkene. In fact, you'll end up with ethene. You'll also make sodium bromide, and you'll also make H2O, which I'm going to draw out because I want to show you exactly where the hydrogens come from. So here's our bromine. Is this going to smudge? Not too bad. And here's one of our hydrogens on the H2O come from a halogenoalkane. Now this is an elimination reaction because, as I said, we're knocking HBr out of this, we're eliminating it. And you get this when your sodium hydroxide is dissolved in ethanol. So it's almost an identical reaction to this one, but a completely different product. When we dissolve the sodium hydroxide in water, we make an alcohol. When we dissolve it in ethanol, we make an alkene. And examiners tend to like these 2 reactions because they're easily confused by students, but hopefully you will remember. When a halogenoalkane is refluxed with concentrated solution of sodium hydroxide dissolved in ethanol, we form an alkene as the only product in an elimination reaction. I say only product. What I mean by that is the only organic product. You also make sodium hydroxide and water, but they're inorganic products. Instead of acting as a nucleophile, here the sodium hydroxide acts as a base, effectively removing HBr from halogenoalkane. Now, if you guys are curly arrow fans, then I'll try and show you what happens here, although you don't need to know this for your exam, okay? So, if we draw a halogenoalkane here, okay, so in fact, I'm going to just show the hydroxide ion coming in from the top here. Now, it'll come in, because it's acting as a base, it'll pick a proton up. Take off that as a proton, as a H+. That will leave its electrons behind in here. And this carbon's thinking at the moment, oh, hang on a minute, I'm about to form 5 bonds. I can't be having that. And so the bromine will leave. And so, if you think about that, H2O, there's one product. Lost that one, so all that's left there is the alkene. And the Br leaves as Br minus, and that's going to join up with the Na plus that was alongside the hydroxide ion. But you don't need to worry about any of that for your exam. Why do we get an elimination reaction here and not a substitution as we saw previously? Because the sodium hydroxide is dissolved in ethanol. Is it in ethanol? Not in water. You wouldn't imagine the solvent would make any difference, but it does. It makes a big difference in this case. Right, test for a halide ion. This you've done at GCSE, but you just need to understand it a little bit deeper here. So test for a halide ion. If you had a halogenoalkane, how do you know what alkane, what halogen rather is stuck on it? What is X? Is it a chloride? Is it a bromide? Is it an iodide? There are 3 steps you need to take in order to find this out. First of all, you need to get the X, the halogen, off the alkane part. You need to knock it off. You need to do a nucleophilic substitution reaction with sodium hydroxide dissolved in water, not in ethanol, remember. So if we do that and reflux it up for a bit, we will form the alcohol, but we're not interested in that in this case. What we want now is our X minus. Now it'll join up with the sodium ion or whatever that was here to form sodium X, but effectively it is X minus. If we knocked it out, we can now test for it. Now we've got this halide ion floating around the place, but we might have some hydroxide ions floating around the place as well if we've added a bit too much sodium hydroxide. So what we need to do in our second step is to acidify the whole thing. We use nitric acid. We use nitric acid in order to remove any excess hydroxide ions that we might have floating around the place. Now, why do we have to use nitric acid specifically? Why don't we use any other type of acid? Well, because if you used hydrochloric acid, say, you'd be introducing chloride ions to the mix, and that might give you an error in the test in step 3 when you're testing for X minus, because that might not be a chloride ion, that might be an iodide. But if you're introducing hydrochloric acid, you're introducing chloride ions, you're introducing an impurity there. So to avoid introducing any impurities to the reaction. Now then, you might think, well, hang on a minute, isn't nitric acid, are there some impurities in there? Well, yes and no, because in the third step, we're going to use silver nitrate. Now, nitric acid is HNO3, silver nitrate is AgNO3. So we've got nitrate ions in the third step anyway, so it doesn't matter that we've got them in the second step. So nitric acid is the way to go here. You add, so you've got the X minus in solution. You add your nitric acid to make sure there's no OH minus in solution. So you can neutralize those. So they're a base, that's an acid. And then hopefully your X minus is going to react now with the silver nitrate. And it might form AgCl perhaps if the X was a chloride. If it did, that would be a white precipitate. If X was a bromide, it would form AgBr, and that would be a cream precipitate. Hopefully this is ringing some bells from GCSE. And if you had X minus as an iodide, that would form AgI, and that would be a yellow precipitate. Okay. Now then, finally, uses of halogenoalkanes. Now, lots of uses for these. Can be used as solvents, anesthetics, refrigerants. However, they're not the nicest of molecules, and their use is tightly controlled. That's because they are toxic and they're not very good for the environment. Now, in particular, they're not very good for the ozone layer. In the 80s, it was discovered that there was a big hole in the ozone layer, and that was a disaster for many parts of the Earth because the ozone layer protects us from the more harmful rays from the sun. So what is ozone? It's a molecule called O3, which protects Earth from harmful UV rays. Some UV rays obviously still come through the ozone layer, but the more harmful ones are protected from reaching Earth. And effectively, this is the Earth's sunblock, if you like. Without it, we would be frazzled, really frazzled. And in fact, when there was a hole in the ozone layer in the 80s, certain parts of the world, we saw skin cancer rates really rocket up. So, what's our CFCs? They are molecules containing carbon. There's the C part. Fluorine. There's the F. And chlorine. There's the Cl. What were they used for? They were used as propellants in aerosols and in air condition units. Keep us nice and cool. So they are very stable molecules normally on Earth, but what tended to happen was because they're gases, they tended to rise up into the upper atmosphere where they were exposed to quite intense UV radiation, and that broke them down. So how do they come to react with the ozone layer? UV light breaks down CFCs, producing free radicals. And if you remember, free radicals are extremely reactive, which react with the ozone layer up there. In the upper atmosphere. Okay, so there we go. Halogenoalkanes in 23 minutes.